Hello everyone. In this video I'm going to do a quick overview of the Mesa 7i76E controller card. I'll cover some things about the card that I had to go look up online to get some clarification on. The Mesa 7i76E controller card is divided into two sections. The left side is the logic section, which includes an Ethernet connector, two expansion connectors, 5 step and direction outputs, an encoder interface with index, an RS-422 interface, and the logic power input. The logic power input here is the most common way of powering the card, the logic section, not the P3 connector. On the right hand side of the board is the field input-output section. There's a field power connector, spindle control that has an analog output for speed control that acts like a potentiometer, enable and direction outputs. There are 16 outputs for the field, 32 inputs, and the first 4 are capable of reading analog signals. The DC voltage input can be anything from 8 to 32 volts. Most typically is 24 volts that is used for the field power, which is what I'm using here. This is the power input connector for the logic section. I'm going to remove the RS-422 connector just for clarity. On the power connector, the upper 2 terminals are tied together and the lower 2 terminals are tied together. The upper 2 terminals are the negative or the ground, and the lower 2 terminals are the positive voltage input, or in this case 24 volts. Notice here that when the 24 volts or the power for the logic section is fed in from this connector, the 5 volt connector here, the P3 connector, is not used. Down here the circuit board has a few components that make up a DC to DC converter. It takes the input voltage here from 8 to 32 volts and down converts it to 5 volts. The 5 volts then feeds the logic section of the board. Now that we've got power taken care of for the logic section, we need to bring power down to the field section. The field power connector has 8 terminals. The lower 4 terminals are all tied together and are the field power input. Any one of these 4 terminals can be used to supply a positive 8 to 32 volts for the higher current needs of the field input-output connectors. The next terminal up, which is the 4th one down from the top, is the V-in. In the most common wiring configuration, this terminal has no connection. We'll talk more about that in a minute. And finally, the upper 3 terminals are all ground, or the negative side of the field power supply. The 2nd and 3rd terminal down from the top are labeled in the documentation as no connection, but I checked with Mesa Electronics and they said that all 3 of these can be used as the field power ground. To bring the 24 volt power that I'm using down from the logic section to the field input-output section, I've installed a couple of jumper wires. I'm using the 2 outside terminals of the field power connector. The upper terminal on the logic power connector goes to the upper terminal on the field power connector, and the lower terminal on the logic power connector goes to the lowest terminal on the field power connector. But any one of these lower 4 terminals could be used for the field power input. Now that I've got the board all wired up, I'll go ahead and apply power. You'll see an LED here come on indicating power to the field input-output section, another LED down here indicating power to the logic section, and a string of LEDs up top here that will turn on and off during the boot sequence. Now I'll get back to this mysterious 4th terminal down, the V-in isolated I/O power. Before I continue, I'm going to remove this lower jumper first. In order to explain the V-in terminal, I need to point out the W1 jumper at the top of the field power connector. In its default position to the left, the W1 jumper connects field power to the V-in terminal. Like the logic section, the field I/O section has its own DC to DC converter made up of these components here. It down converts the 8 to 32 volts applied to the V-in terminal and provides 3.3 volts to the field I/O processor. The W1 jumper was never intended to carry the higher current that's possible in the field input-output terminals. Because of the current limitations of the W1 jumper, field power should be applied to one of the 4 field power terminals. This allows the full current of the field power supply to be available for the field I/O terminals. To power the field I/O processor, power will flow from the field power terminal through the W1 jumper and up to the V-in terminal. This way there's only 30 milliamps or so flowing through the W1 jumper. And next, I'll talk about a scenario where the field power is separated or isolated from the V-in. And once again, I'm going to remove this jumper before I get started. For this setup, we're going to assume that we're wiring up the board to a machine that requires 5 volts on the field inputs and outputs. The first thing we're going to do is move the jumper from the default left position over to the right hand position. This separates the field power terminals from the V-in. Now there's no electrical connection between the two. Now, with the input power isolation taken care of, I'll apply 5 volts to the field power. Here I have 2 wires that go to a 5 volt power supply. The black wire is the negative or the ground, and the orange wire goes to the positive terminal of the 5 volt power supply. I'll start by connecting the negative to the second terminal down on the field power connector. This shares the ground with the 24 volt power supply I have connected to the logic section. Next, I'll connect positive 5 volts to the 5th pin down on the field power connector. This supplies plus 5 volts to the field power terminals, as well as provides 5 volts for the field outputs and sets the sensing voltage for the field inputs to 5 volts. With the field power taken care of, I'll turn my attention to the V-in terminal. Since the DC to DC converter requires a minimum of 8 volts to operate to power the field I/O processor, the 5 volts that's now on the field power terminals is not enough. So I'll install a jumper to bring the 24 volts that I'm using over from the logic power connector to the V-in terminal. This configuration provides 5 volts for the field input output, and at the same time providing a high enough voltage to operate the DC to DC converter for the field processor. Using 5 volts for the field input output is not recommended since it's much more susceptible to noise, and it is also just less reliable because of the reduced voltage swing from 0 to 5 volts versus 0 to 24 volts. A higher field voltage is also more reliable for contact type inputs such as mechanical push button switches, micro switches, and relay contacts. There are 2 versions of the controller card. This one is a 7i76E, which has sourcing outputs. There is also a 7i76ED. The D designates that the outputs are syncing outputs. So, as an example, using this card which has sourcing type outputs, if I wanted to activate this solid state relay, I would connect the positive lead to one of the field outputs, and the negative lead would be connected to the negative bus of the field power supply. In contrast, the ED version of the card has syncing outputs, and it's just the opposite. The solid state relay's negative terminal would be connected to one of the field outputs, and the positive terminal would go to the field power supply positive bus. From what I found in my research, the ED version of the card is typically used for retrofitting older equipment that was originally configured for syncing outputs. For a new build, the preferred method is to use the sourcing outputs of the 7i76E card. It's important to note that the syncing outputs of the D version only apply to the outputs. The inputs on both the E version and the ED version are the same, and they sense a positive input. The positive sensing inputs bring me to my next topic. I'll be using inductive proximity sensors for the homing switches and limit switches. When using proximity sensors versus microswitches, it's best to use PNP type. The PNP type proximity sensor will provide a positive signal to the input versus the NPN type, which provides negative signals. And finally, the last thing I'll talk about is the step and direction outputs. This card supports both single-ended and differential outputs. I spoke with the very helpful tech support at Mesa Electronics, and they recommended that most stepper motor controllers be driven in single-ended output mode. The differential mode is primarily intended for servo motors, which have differential line receivers. It's important to check the documentation of the stepper motor driver, as many of the more economical ones don't support differential inputs. First up is single-ended mode using a common ground. For this connection, I created a ground wire where the end that connects to the stepper motor driver has a built-in jumper wire. This provides a ground signal to both the step or pulse negative as well as the direction negative inputs. The step positive and direction positive inputs to the stepper motor driver are then connected to the step positive and direction positive outputs of the Mesa card. This is typical wiring for single-ended mode using ground as the common. The stepper driver can also be wired up using plus 5 volts as the common. In this case, the step positive and direction positive get a continuous 5 volts supplied, while the step negative and direction negative are pulsed by the Mesa card. I have a bit of a conundrum wiring up my stepper driver. Mesa Electronics recommended that I wire it up in single-ended mode, but the documentation that came with my driver recommends line driver mode or differential mode. I suspect that either mode will work perfectly fine, but since I've already made up the cables for running in differential mode, I'm going to start with that and see how it works. Here's how I'm wiring up my stepper motor driver for differential mode. It's pretty straightforward. You just wire up the pulse and direction positive and negative on the controller to the positive and negative on the driver. Well, that's all I've got for now. Subscribe if you want to follow along. The last few seconds of the video are some images of the 7i76E Mesa card. It highlights some of the features. Enjoy!